Let's talk about graphs of some basic functions. So we're about to see about half a dozen or so graphs of these functions that we will be working throughout the course and of course your future courses. They're very common, very popular. We're going to look at these functions in their most basic form without what I call any bells or whistles attached to them, in their most simplest form. But before we do that, I want to mention this idea of continuity of functions, which is a big deal in mathematics and in the future work that we do. So let's begin with informal definition. Again, this is not a formal definition, and you can read it from its definition. It's not the formal definition about continuity, whether it's at a point, at an open interval, closed interval, endpoints of an interval, so on and so forth. Usually those are addressed in a first semester calculus class. So for now, our definition is this: a function we're going to say is continuous. When you graph it, you don't lift the pencil from the paper. Now, of course, nowadays a lot of people don't use pen and pencil, but in general, the idea is that, for instance, if I have the function here, call this xy, I'm just graphing something random. Notice how I'm moving my pen on this screen, and I did graph this function without lifting my digital pen. Okay, so that's the idea of continuity. There's typically, if the function is continuous, that means there are no breaks in the graph, there are no holes, there are no jumps. So for instance, the function could have a hole in it, there you go, and a jump. So this function is not continuous. Another example, simply it would have some hole here and then maybe continues on in another segment. And I could have also discontinuity that maybe, for instance, in this form, I could have a function that behaves this way. There you go. This time the discontinuity is along this vertical dotted axis. So there are several ways discontinuities could occur. So the one that I graphed initially, this is an example of one that is continuous. That's the only one. This one is not. This one is not, and this one is not. Okay, so having talked about those, we're going to look at graphs of functions that are continuous in this segment. Okay, so let's start. We're going to begin with the most, again, the easiest function that we can find is probably what we call the identity function. The identity function. So let's start with that. We're going to look at our first function is the identity function. The general form of the identity function is f of x, the notation for all functions, and you simply have an x. There you go. Notice the identity function is a linear function, so it fits the general structure of linear functions that are in the form mx plus b that we talked about earlier in another video in the earlier sections, section 2.4, I believe that was 2 videos back. So here's a case where m is 1 and b is 0. And those are special cases of the identity function. So it's just a linear function. Now for these functions, what I like to do is I like to give you first the graph of them, and the graph of this one would be a line, 45-degree angle line that runs through the origin. So here's your x, there's your y, and this is the graph of f of x equals x. So there's a graph. Now other information that we are interested in: the domain of the function, which I'm going to indicate using this notation. The domain of this linear function, like almost all linear function, is from negative infinity to infinity. And so is its range, right? So we're interested in domain, we're interested in range of f, also from negative infinity to infinity. And then whether the function is increasing or decreasing, we talked about those also previously. And this function, now to determine increasing or decreasing, we always move along the x-axis, right? We go in this direction. along the x-axis, from very low to ultimately very high. So as we move from left to right, let's see what happens to the graph. So I'm holding the pen on the marker as I'm moving from left to right along the x-axis. So I'm going in this direction actually. And notice when I do that, the function is increasing. As I continue on to the right, the function is ever increasing. So it seems like this function is always increasing. So keep in mind, to determine increasing or decreasing, you look at the domain of the function, and then you move from left to right on the x-axis and look at the behavior of the function as you go. Usually, if you hold your pen, pencil, or your cursor on from your mouse, you hold your cursor over the function, you can actually visually see the behavior of the function. So for this one, again, it looks like the function is always increasing, never decreasing. Therefore, I'm going to just put increasing, and this time from, again, negative infinity to infinity. Again, this is along the x-axis. We're not talking about the function, we're talking about where. This is over on the x-axis. This is over the domain, okay? So as you go from left to right here, the function is always increasing. All right, so there's our first function, the identity function. Next, let's take a look at our, what we call the squaring function. The squaring function, again, its most basic form is f of x equals x squared. Now, what does the graph of this looks like? Where this graph, I'm sure you've seen it in your earlier math courses. This is the graph of the function. The name of the graph is a parabola, right? That's the name of the graph. A parabola. We take a look at these parabolas in much greater detail later on, but for now, there you go. That's the graph. The domain of this function, the squaring function, again, x can be anything along the x-axis. Remember, for domain, we look at possible x values along the x-axis. X can be anything. You plug it into here, you square it, and there will be an output for every given x. So the domain is going to be negative infinity to infinity. The range of this function, if you look at, remember the range, we look at the y values, right, along the y-axis. It looks like the function is always going to be above 0 along the y-axis. So the range is going to be from 0, including 0, that happens when x is 0, 0 to infinity. Increasing, decreasing, remember to determine increasing, decreasing, we go from left to right along the x-axis, right? And as we go, let's see, the function is going to be, check out, follow my red pen. As I go from left to right, you see how this function is decreasing, decreasing up to 0. And then it picks up beyond 0, it's always increasing. All right, so we're gonna mark that. Then I'm gonna write that the function is, remember we go from left to right. So as we go from left to right, function is decreasing. And is decreasing from negative infinity on the x-axis up to 0. And because for increasing, decreasing, we agreed to use open interval because we define these over open interval, the concept of increasing, decreasing function, not at a point. So we don't include a bracket at 0. Some textbooks do, again, some authors, some professors do. I'm just going to follow the common convention of the majority of authors and textbooks and professors that do not include the parentheses. Okay. Now, increasing, I mentioned as I moved my red pen over over here. Remember that segment? The function is increasing from 0 to infinity. And it's never constant. Never constant. And there we have it. So we have our squaring function. Now let's take a look at our next function. We're going to go to following squaring function. We're going to look at our cubing function. Now the cubing function, this one, f of x is going to be x cubed. The graph of x cubed in its most general and simplest form, by the way, is going to look like this. And there we go, roughly, that's what the graph looks like. So this is x cubed. And for this function, again, the domain of f, x can be anything, right, along the x-axis. You can always put in a number, negative, positive, 0, and you'll be able to cube it. As long as the operation can be done, domain is all real numbers. So domain of this one, negative infinity to infinity. The range of this function, also, if I look at along the y-axis, I can always, you see, there's always a y for a given value of x. The graph exists. So you see here, there you go, there, here, these, all the graph exists. So the range is going to be also from negative infinity to infinity. All right, and we got that part. Let me tidy up this and clean up this portion, redraw the part that I just removed. And there's your basic x cube function. Domain range, increasing, decreasing. So remember, for that information, I'm going to go from left to right along the x-axis. And then as I do that, if I go along the x-axis, let's trace the function, see what happens. So I'm coming from negative infinity, increasing, and it looks like it's always increasing, true? As I move from lower left to upper right side. So it's always increasing, therefore, we're going to put that the function is increasing always. And that we show as negative infinity to infinity, always increasing. The cubing function. Next, we're going to look at the square root function. This would be the fourth one that we're looking at. The square root function, f of x is equal to root x. That's what that one is. The general form of the graph, again, you could plot points on these, by the way. But for what we do later on, we're always going to be graphing the general shape like this. There you go. That's what the square root of x looks like. You can form a t-chart here, for example, put 0, 1, 2, 3, 4, and get the numbers, plot points, and that's what you're going to get. We're looking at the general shape of that graph. So here's our square root function. Now the domain of this function, if you note, the graph starts at 0. So I don't have any graph on the left side to the left of 0. So this would be the domain of this function, right? That is our domain. What about the range of this function? Again, looking at the y values, the range looks like y. This would be range. Y is going to be positive, so both x and y will be positive for this. And as far as increasing, decreasing, let's do that part. We go from left to right as you move along the x-axis. Let's see, and of course, remember, we don't have this part because we start at 0 over the domain. The movement is over the domain from left to right, right in here. Because again, there's no graph to the left of 0, so I have nothing to the left of 0 on the x-axis. Now, as I go from left to right on the x-axis, again, look at the marker, how the marker is moving on the graph, and it's always increasing. Although it has increases ever slowly, but nonetheless, it's increasing. And we're going to write down all this information now. The domain of the function, therefore, is from 0, including 0, because square root of 0 is 0. The range of the function is also from 0 to infinity. And so that's domain, that's the range. What else? Increasing, decreasing. This function is always increasing. And it's like, well, what's the big deal of that? It's good. It's because we talked about increasing, decreasing constant, so might as well talk about this idea also. So it's going to be increasing from open interval 0 to infinity, never decreasing. And there's our square root function. Now, once we go from square root function to the next one, this next one is going to be the absolute value function. Now, the general form of the absolute value function is absolute value of x, like that. Now, the absolute value function, again, here is, suppose this is my x, y coordinate system. Here's 0. The basic absolute value is going to be a line like that. And the reason, by the way, is because absolute value of x, remember, is x or negative x. If x is greater than 0 and x below 0. Well, x is just the identity function, right? Remember, that's this function that I did the very first one. But it's only good for greater than or equal to 0. So that's why I maintained that segment of that line. And for negative x values, it behaves as negative x. So think about negative x plus 0. The graph of this function. Slope's negative 1. Y-intercept is 0, which is really 1, 0 as a point. X is 0, oh, sorry, 0, 1. There you go. Oh, 0, 0, so sorry. Because when x is 0, y is 0. There you go. Remember, the y-intercept is a place where x is 0. So when x is 0, y happens to be 0. All right, and that's for this one. So it's going to be also another line, just like the one I drew. This is another 45-degree angle line. And that's going to be the graph of the absolute value of x. All right. Now, what is the domain of this function? Well, you can put any real number into the absolute value. It will be able to calculate it. So it's negative infinity to infinity. What is the range of the function from the graph? Remember, the range are possible y values. And those are from 0 to infinity. The range is 0 to infinity. Now, for increasing, decreasing, again, we move from left to right, correct? We go in that direction along the x-axis. And as we do, we're going to trace or track, I should say, the function. So it's coming from way up there. It's going in this direction. So decrease, 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 stops and bounces up, increases. So we actually have 2 segments here, right? The function is decreasing from negative infinity up to 0. And then it begins to ascend or go higher, increasing as it goes from 0 to infinity. And there we have the graph of the absolute value of x. Okay, and those are pretty much the ones we want to talk about for now. There is one other graph. This is not a function. So let's say this is a relation, however. Remember, a relation is an ordered pair in a set. At least one, could have many. So this next one is not a function, but it is a relation. It's given by x equals y squared. Now for this one, just because it's the first time we are doing this, let's say, here's x, here's y. Usually we pick values for x, determine the y values. This time I'm choosing values for y and seeing what x's turn out to be. That's going to be 4, 1, 0, 1, 4. Okay. And now if I plot these points on the Cartesian coordinate system, here's x and here's y. So x values, they're going to be 0, 1, 4. So when y is negative 2, let's say here's 1, 2. When y is negative 2, x is 4. Here's 1 point. When y is negative 1, x is 1, 0, 0. And then 1, 1, and 2, 4. So when y is 2, x is 4. There you go. So I've got these 4 points, right? Now I can connect these 4 dots, right? Using not a straight line segment, but using a curve. There you go. So we have this portion. And then if I use a curve, smooth curve, I get this other portion. And these are the points that were on the line there. So it looks like a parabola on its side, right? Like y equal x squared, only on its side. And it's interesting, x equals y squared. Y equal x squared is when you actually switch the variables. You get switch one, you get the other one. The effect of that switching x and y is to cause the graph to go from the way it was to the way it is now. It gives it like a 90-degree rotation, right? Almost. But we'll talk about these later on. It will actually cause the graph to reflect. Now, we'll talk more about these when we talk about the inverse functions. All right, so there you go. This is going to be the last one. Now, because if I do the vertical line test on this one, check this out. There you go. Remember, vertical line test tells us if we draw a vertical line and it crosses the graph of that relation at two or more points, then this relation cannot be a function. So that's why I just called it a relation, not a function. That is not a function. So the things that we could do with a function, we are not allowed to do with this. And remember, all it takes is for the relation to have two ordered pairs that have the same first components. And you can see for this one, for instance, when x is 4, y is 2. When x is 4, y is negative 2. Correct? Right in here. 4, negative 2, and 4, 2. So in those two ordered pairs, see, those are the same. So this relation, this implies that this is not a function. But we do work with this eventually at a different capacity, so it was worth mentioning it. Now the other thing here, these are really the basic functions I wanted to talk about, but let me go back up here and actually try to box these. So here's one. Here's the other one, the squaring function, the square root function. This was the cubing function, and this was the squaring function. And the very first one was the identity function. Again, we should keep track of these functions and try to reference them as often as you can, just so they stay with you, because we will be using them quite often in our future work. Okay. Now the last idea, and then we look at some example here, is let's talk about this idea of what we call piecewise functions. So what is a piecewise function? Well, a piecewise function is one that's made up of several pieces. Okay, so for example, just on the graph of a function, and then I'll give you one with details algebraic expression. So for example, I could have a piecewise function that looks like this. It could be, let's say, a line up to here, then it switches to a parabola, and then it goes to a line. So it's coming, and then let's make it, I don't know, and then it goes flat lines. So that would be a piecewise function. So this function is made up of 3 pieces, right? What are the 3 pieces for this one? Here is the first piece of that function. This one is the second piece. Actually 4, I'm sorry. This would be the third piece, and this is of course the last and the 4th piece of the function, and hence properly called a piecewise function. Now let's take a look and see, for example, how can I graph these when I'm given what the form looks like for the piecewise function. So an example of a piecewise function, I'm just making something simple up. So let's say I'm going to have 3 pieces for this function. I'm going to call it x squared, the ones that we just talked about, and a linear function, negative x plus 7. Now, the first function is good when x is negative. For values of x between x0 and 2, inclusive of 0, exclusive of 2, it's governed, the function is governed by a parabola. And for values that are 2 or higher, exceeding 2, including 2, it follows the line. So if I graph this function now, here's the x-axis, and this is going to be, let's say, the y-axis. So the first part, again, is the identity function. Remember, the identity function looks like this, correct? The reason I made this other part of it dotted, because the identity function is good only for negative numbers. So we don't actually need this portion of the identity function because it's not valid for anything 0 or higher. So at this point, I actually have an open circle here, don't I? Because it does not include it. However, the next piece, which is a parabola, the quadratic function, when x, because this one does allow for equals 0. And when you put 0 in for x, 0 squared is 0. So this 0 actually fills in the hole that the identity function left. All right, and so putting all this together now, I'm gonna actually remove the circle here, and it's gonna be filled. Think about this circle, by the way. How big is a circle? It's about the size of 1 pixel on your screen. Even that is too big. So that's pixel, the size of a pixel is filled with a dot, a single dot of same size. Now, then this is a parabola for the next segment. Well, the x squared function, remember, it looks like this. However, we don't want this portion of it because this is only good for between 0 and 2. So I'm going to erase this part of it. And between 0 and 2, let's make it like that. This is 2, and when x is 2, 2 squared is 4, right? Plug in 2 for x, you get 2 squared is 4. Therefore, the height at this point is going to be 4. Now, it doesn't include 2, so at this point I actually don't have a closed dot, right? Let me redraw this one. There, so that's what that looks like. I will have an open circle at 4, meaning 4 is not included. The reason, because 2 is not included. Now the next piece is a line, the graph of negative x plus 7. Again, this is the y-intercept, and the slope is 1, right? Remember, we use m for slope. Slope's 1. Okay, so y-intercept, or negative 1, sorry, it's negative x, negative 1, which means the orientation of line is like that. And for this one, because this is good for greater than or equal to 2, so I'm going to actually plug in a 2 here. Negative of 2 plus 7 is 5. So when x is 2, y value is at 5. So it's right in here. And the slope's negative, y-intercept 7. A negative slope, I know, is going to look like this. A 45-degree angle, or just like the identity function, only going in the opposite direction. The other side of it goes like that, doesn't it? Which ultimately crosses at 7, the y-axis. But we don't care about that part of it, right? And the reason we don't, because our domain for this third function, our domain is for greater than or equal to 2. So we only look at this segment of the number line. And there you go. This is what a piecewise function looks like. Okay, and that is the graph of a piecewise function. Of course, I have arrow here. And there you go. Pretty cool, huh? So let's take a look at now some exercises together here. I'm just going to, again, make up some examples and then look up some examples or exercises and work them for you. All right, let's take a look at a piecewise function. Let's see how we actually calculate values, different values of x. How do we work it in a piecewise function? So my piecewise function, it's going to be f of x equals we'll have three pieces. Let's say we make it 2 plus x, we make it negative x, and we make this 3x. Linear functions. This is when x is less than, let's say, negative 4. For between negative 4 inclusive of 4 and inclusive of 2. Then the function behaves like a negative x does. And it behaves as 3x for when x is greater than 2. All right, now we don't have to graph this one. We'll do this in the next example I make. For this one, I just want to do, for instance, let's do f at negative 5. I just want to know which function, which piece am I supposed to use. Well, negative 5, you have to look, remember, this is your x values, right? In this case, just a single value, x value. So I'm going to look at which domain is the, I'm not even looking at these functions yet. I'm just looking at the x values. Where does this negative 5 fit under? Well, is negative 5 greater than 2? No, so it's not going to be that piece. Does negative 5 lie between negative 4 and 2? No, because negative 5 is less than 4, negative 4. So it looks like it fits under the very first function, right? And because that's the case, I'm just going to go 2 plus negative 5, and that's going to be negative 3. You see that? So that's how we work these. Find the value of the function in that piecewise function. Let's do, for instance, f at negative 1 now. Well, same thing, and we're going to run it through here. And only one of these, by the way, these domain values are distinct. They're non-overlapping. We call these mutually exclusive segments on the number line. So negative 1, is it bigger than 2? No. So it's not going to fit in there. Is it between negative 4 and 2? Yes, because negative 1 is to the left of 0. So there you go. That's the one. And it doesn't fit as something less than negative 4. So it's not in the first one. Therefore, this fits into the second function. That's going to be negative 1. The value of the function is 1 at that point. Okay. And let's see. Let's take a look at, for instance, now, what about f at 0? Well, f at 0 greater than 2? Nope. 0 is between negative 4 and 2. True. That's true. So it's going to be negative of 0, which of course 0 doesn't have a sign. Positive, negative, 0 are the same, and there we have it. The next value of the function, I'm going to try maybe, how about f at 3? Because I haven't used the last function. Now 3 exceeds 2. So I'm going to use that piece, if you will. It's going to be 3 times 3, because you plug in 3 here. And that's going to be 9. So the value of the function using the last piece is going to be 9. So that's how we evaluate the points for piecewise functions. All right. Now, let's say I want to graph. How about something like this one? Something simple, but makes us graph something that we've talked about before. Suppose for x less than or equal to 1, I have negative 3, and for x equals, f of x equal negative 1, this has got to be bigger than 1. See, I'm making sure that there are no overlaps in our domain values here, right? So, in other words, I cannot do this. They both cannot include 1. One of them has to exclude it. So I just picked the first one. Now let's take a look at the graph of this function. Here's x and here's y. Now, f of x equal negative 3 for x less than or equal 1. So here's 1. That's 1 when x is 1. Negative 3, 1, 2, negative 3 is this one. So it's going to behave as a constant function at negative 3. And here you have it. So this is f of x equals negative 3. Now, that's over the entire domain, right? We just said this is only good for x less than or equal 1. So only this piece, right? For less than or equal, only the left piece of that graph is going to work. Therefore, I'm going to erase what's to the right of it. Now for x greater than 1, x bigger than 1, means everything on this side now, to the right of 1, it behaves with a different constant function. That constant function is -1. And again, suppose this is -1. But then this is only good for when x is greater than 1. So I'm going to have an open circle at 1. Let me do that a little better. Open circle. And it's going to be only the right side. So we don't need the left side. You see that? And therefore, this is the graph of that piecewise function. And my open circles are, this one is okay, close one. This one's a little big, but yeah, that's okay. As long as it's just the small, again, this is really the size of a pixel. That's what it is. And there you have the piecewise function. Okay. Now, and let's see, I just did one up there, piecewise example also. What else? Let's take a look at one for like discontinuous function on the graph. So I'm just making up one, and then we'll be done with this video. So here's an example of a function that has discontinuity. There you go. The function is continuous until it hits a. And then after that one, I may do something like this. So notice this function is not continuous at a, right? So at x equal a, f is discontinuous. All right, f is discontinuous. And there we have that one. All right, so hopefully you were able to follow everything about this section, and that's all we wanted to do. Graphs of basic functions. And we are done with this video. Again, thank you for watching, everyone.